probably it is cubic shape, but you can always change in x and y
Yes.
to different size, right? Try not to use nx, ny, and z of the same dimension because sometimes when we, for example, if we get to the flow field in this kind of three-dimensional space, and we may want to say, let's look at the flow. Let's say, in the question we have a sphere, right, at the center, and the thing it is, if we want to look at, for example, if we want to look at the velocity profile or velocity distribution in this kind of plane, right?
Yes.
And we say that we have x direction u, y direction v, z direction w in this plane. Either one, and we save to let's say u dot dat, right? And if we save this one and open in the Excel in MATLAB, we will have this one. Let's say if you use 100, 100, 100, you will have 100 by 100, right? Because it is, right now you only look at this two-dimensional surface, right? But sometimes this one, it's a little bit confusing. I'm not saying it is wrong, it is a little bit confusing because you are kind of, let's say, this is the x direction, this is the y direction, and this is z direction, right? So this plane, basically, it is the xy, xz plane, right? Because y is fixed at here, right? And in that case, sometimes it is confusing or it needs some time to, to figure it out. So is this x, is this z, or is this z, is this x, right? Yes, if you look at your C program, how the data was saved, yes, definitely you can tell. But if you say, I'm going to use nx equal to say 120, and nz, let's say it is 110, and ny, let's say 100, right? You're not going to be confused. And right now, either you say, when you save this kind of, you fix the y and look at here, you either have a 120 by 110, either 110 by 120, right? And now if you look at here, so this must be x, this must be x, something like that. Try to not use the equal size. And so you can easily identify which direction is for which dimension, right? So look at this program. You can leave the solid object there, or you can remove it. Remove it, and if you look at there somewhere, we say if like the position, I think it is called the in fluid, right? And we have if r is r is less r, then it is a solid. Otherwise, right? You can in this one you can always say it is it is always a fluid. Then you do not have solid object. But for this point, you can have this one there. You can remove it, and I think it's better to remove it. Remove it, and also so let me say currently what we have. So this JCP 3D LBM program, right? And right now it is a solid particle in the center, right? So what I want it is, so that is the current one. So let's remove it. Okay, so that is one change. Another thing right now it is the flow generated by a body force. So right now we have a solid particle, and the body force, it is a G applied to every lattice node, right? So we are going to, right now so you cannot only do this one and run the program again, because before you have a solid particle stays here, and then basically it is kind of object or obstacle, right? The flow going around this this solid structure.
Yeah.
If you do not have this one and it is periodic everywhere, so that means, so before, if we look at 2D, it is one cylinder, something like that,
Yeah.
right? And then you apply a body force. So that means basically it's like the water or something going through this kind of a forest or something, right?
Yeah.
And the water will find, eventually they will negotiate a balanced equilibrium state, because water wants to go this one,
Yeah.
but the tree wants to stop them.
Yeah.
And the thing it is, if you cut all the trees, and everywhere is water, and then you simply add this one, so the water velocity will going up, going infinite, because there is nothing to hold it back, right?
Yeah.
Physically, you are just keeping kind of pumping energy in it, but there's nothing to.
Yeah.
So you cannot have this one anymore. So right now you need to say body force. You need to set this one to be zero.
Okay.
Okay?
Yeah.
But right now, if you look at here, then you do not have body force. You do not have structure.
No.
So it is nothing, right?
It is
nothing. It
yeah.
is infinity, but nothing. So what I want you to do is, the first thing it is, so you may want to think about to generate a shear flow, right? Generate a shear flow by using the method we are talking, okay? So, and without putting anything there, just a pure box. And in this way, because we are going to do the shear flow in the z direction, so the y direction, if we are going to have a particle like a real, sphere, and let's say the diameter is 10, and then the y direction, at least it should be 10, right? But right now, let's do pure fluid.
Okay.
So the ny, so because we do not want to, especially with your current laptop, I will think about to clean up a little bit of the old laptop I had before, just to get the files, because you need a Windows laptop, okay? And the ny can be small. The reason it is because the direction y, it is going to be the same. It is going to be the same. But right now, if you have 10, 20, sorry, it's like 120, 120. It is just wasting time repeating the same thing. And you may want, but ny you still want to keep the periodic direction. So usually we see at least make it 4, 5, 6.
Okay.
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 So basically we are having a very thin layer. Okay, but not technically you can have this one to be 1. But 1 is a little bit tricky. So let's because if we only have 1, so if we look at the side view, so basically in the then we have the, if we say this is the y direction, and so this will be 0, this will be 1, this will be 2, this will be 3, this will be the ny minus y, right? Yeah. And the periodic in the y direction, anything goes here, anything goes here, right?
Yeah.
And if we only have 1 lattice nodes in the y direction, then the thing it is, this guy is going to come back to itself. Yeah. Right? And so that, if you do them correctly, it will be fine. But sometimes it is, pretty easy to make some mistake. Okay. So it is better to keep the y at least 2, 3, something like that. Okay. Okay. And then look at the period. What we say, the Leeds-Edwards boundary condition. Okay. And now we should be able to do, just a pure shear, just a pure shear. And so what we still have the regular, so to develop this program, you need to define, you need to introduce the gamma,
Yeah.
right?
Yeah.
Whatever you want to put. So gamma usually, if we think about the, if you think about the, because it is going, if we look at the front view, so this would be NX, this would be NZ, right?
Yes.
So we want to have a shear flow pretty much this way. And remember we mentioned in lattice Boltzmann the velocity should be no more than 0.01. Usually we say 10 minus 3 in such an order, right?
Yeah.
If we say 10 minus 3, and this one we do not know exactly how much, let's say this one is approximately 100. It could be 110, as I said, 120, but roughly 100, right? So the gamma here, it would be, if we look at here, so the gamma should be, if we have a u over, if we have a u over here, if we have a u over here, so gamma it is twice of u divided by nx, right?
Yeah.
Nz, sorry, right?
Okay.
So it is velocity changing from positive to negative over this distance. And this one, as I said, if we get an estimate, it is twice 10 minus 3. If we want u to be around 10 minus 3, right? And here it will be 100, right? So that means twice 2, 10 minus 5, something like that.
Yeah.
So, and so that is, give us an idea, so how much we should put the gamma. And let's say it is 10 minus 5, right? And we can always change it, right? We can always change it. You define nx, ny, nz, you put this one. And you modify this one other than, remove the particle, set the velocity, set the body force to be 0. And now you run the program, and the program does nothing because you have no flow, you have no structure, right? So with this one, what you need to do it is, remember, if we look at the basic lattice Boltzmann algorithm, it doesn't matter where we start. It is, let's say, if we say this is a collision. After the collision, we have the lattice density distribution going to different directions. It is a propagation, right?
Yeah.
And inside of the propagation program, and we have, basically ways. So the current propagation with periodic, right? Boundary in both x, y, and z directions. That is the current of the program, what the program is doing, right?
Yeah.
So basically the propagation moves the lattice density distribution from this point to next point, from this point to this the next point in the same direction. And then after this one, and we go, next thing it is, we calculate rho u, right? And after this one, so it's not very organized, we calculate the FEQ, right? And with those things, and then we do the collision.
Yeah.
We get the collision, and then, so that is the current lattice Boltzmann program. So we keep doing this loop again and again and again. So this one we do not, this is the current program, we do not have the Lees-Edwards boundary condition. So it cannot generate the shear flow, right?
Yeah.
So in order to generate the shear flow, so in the propagation, I talked to another Jipeng, and you think about something. If you want to modify a program, there are two, for example, people say, let's say we are calculating the sum of A and B, right?
Okay.
And then we do double A, B, right?
Yeah.
And then we say, let's say A equals 3, b equal 5, right? And then we say print a plus b, right? Something like that. It will give us an 8, right?
Yeah.
So right now the program say it is 8, and I said, I want to change the program instead of 3 and 5, it is, let's say, 3 and 10.
Okay.
Okay, 3 and 10, you said, clearly we need to change the value for b,
yeah.
right? So there are 2 ways. Either we say, let's get rid of this one and say 10, which is correct, right? Or, sometimes you may say, later on we probably want to redo, right now it is just 3, 5, it is just one character, but sometimes it is a large portion, right? You may say, probably later on we want to look at the 3 and 5 again. So what you can do, it is, okay, A is 3, B is 5, let's do this way.
Oh, yeah. Okay.
Right?
Yeah.
So yes, you may argue, so this is kind of a waste of time, but forget about this 10 minus 5 seconds, right?
Yeah.
So let's do this one, and so same thing like we change your program.
Yeah.
Originally you have a function,
Yes, and
right?
Yeah.
I said comment this one out
And
and
then
say of shifted
Yeah.
x equal to 99.2, right?
Yeah.
And we can leave this one there, right?
Yeah. And
Yes,
still
it
work.
will calculate something, but whatever you get, I will overwrite whatever you have,
Yeah.
right?
Yeah.
So the concept here it is, if you want the program to be, if you care the efficiency, you really care the calculation time, so it's better to disable, do not do if any unnecessary calculation exists, just do not do it.
Okay.
Okay? And on the other side, if the calculation time is not a big issue, let it do it. Whatever it calculated, I will, some of them may be correct, some of them may be not. I will redo the incorrect ones. I will keep the correct ones.
Yeah.
So either way. So that is what I'm saying. The current propagation program that we have, it is a regular periodic. This is not exactly what we have. But if you look at here, so if we just do the two-dimensional diagram, so what this one has been done, it is, for example, so they have sent those things exchange correctly, right? So most of the stuff that finish in this part is correct. Even if we have this one, it is going to be here, right? If we have this one, it is going to be here, which is correct.
Yeah.
The only thing not that much correct, I don't have a different color, it is if we have a top one. And the top one, if it goes this way, this is okay, right? If only this one, it should be shifted up here, right?
Yeah.
So remember that the current propagation is doing 99% of the job correctly.
Okay.
It finished all the things 100%, but at the end, the 100% of this job, 99.5 is correct.
Okay.
And there 0.5
That is incorrect.
is not correct. We need to do that,
Okay.
right? So it will be easier to just say, add a new function, say it is lead and was boundary condition, something like that.
Okay.
So that means let this regular propagation program function stay there without changing anything. It finish all the propagation 100%, 100%, but 99.5 is correct.
Yeah.
0.5 is not correct. So I will do the 0.5 correction
Here.
over here.
Okay.
So here I will focus on the lattice directions going to across the boundary.
Okay.
And right now your program, the current program, you are splitting this kind of things. One is crossing the top boundary, one is crossing the bottom boundary. So you may even want to say, I want to do this one in 2 parts.
Okay.
Right? The end was, let's say up
Oh, okay.
right? And then the adverse bottom, right?
Yeah.
So I'm not sure, if you say, because if it is going up, that means it's going to come back from the bottom. If it is bottom, it's coming back from the top. Whatever you do, one and another one. So if we have these things, there are something, most of them are correct, some of them not. I will correct a part of it, I will correct another part of it.
Okay.
Right? So those things are already there. We just need to do this one.
Okay.
Right? So what we can, if we, let's quickly, look at how what we need to do in the program. So if we take one, right?
Yeah.
Right? So let's say, assume this one it is to, for Fi's, right? So basically, remember, this is for the post-collision things.
Okay.
In our program, I think the post-collision that, if I can say it here, it is basically, the F temp, right? So the F temp, and the F temp is going, so for F temp, right? F temps going out from the top boundary, okay? Because it is going up, right?
Yeah.
Okay, so the first thing we know, for anything crossing the top boundary, it must be the very, very last layer, right?
Yeah.
So Iz must be Nz minus 1.
Yes.
It cannot be anything else, right?
Yeah.
And then the X and the Y, it is for everything,
Yes.
right? Even Iy right now, we may only have 4 or 5, we still need to do the loop, right?
Yeah.
Okay, so, and then the IQ, we do not need to do IQ for everyone, because even for the top one, so this guy doesn't need special treatment, because it goes this way, right?
Yeah.
And this guy, it is fine just to go here.
Yeah.
So which one is going crossing the border?
That one.
If it has, so for IQ equal, you even want to start from 1, because 0 is going to stay there,
Yeah.
right?
0, yeah.
Yeah, and NQ. And over this 1 to NQ, not everyone. So if to going up, so that means E Z direction, right? This one must be 1,
Yes.
right?
Oh, yeah.
So if we do the layered loop up to here, so we can see right now, it is only for F temp going up, right? And now we can think about, you can apply what the small functions you have already developed, right? So right now it is, so what our job it is, okay? So I will write in, not exactly like the code, just the description, right?
Okay.
So it is from, right?
Yes.
From Ix, Iy, and Iz is Nz. You can see Iz, or you can see Nz minus 1,
yes.
right?
Yeah.
In the Iq direction, right?
Yeah.
So that is where it from, right?
Yeah.
And the new, I think there's one thing we haven't mentioned yet. So the new, so this one is going to from this point, and so this is from the top going to. I kind of confused, not exactly sure. It is Ix. So I think we have, you know, if we follow the way that we have in the propagation, we have the xd, yd, right? Zd, right?
Yeah.
So, but right now, originally, those things are kind of declared as integers.
Okay. Yeah.
And we can still have these two integers, but x
Can be real.
is a real,
Yeah.
right?
Yeah.
So you may still, you know, keep this one because y and z it won't change, right?
Yeah.
And this one should be a double.
Yeah.
So this one, zd we know. Right now we are talking about something going up from the very bottom,
Yeah.
very top.
Top to
So
bottom.
either way, it is this one must be there,
There.
right?
Yeah.
And the yd we can still do that one because in the y direction we are still doing exactly what the periodic it is, right? So yeah, I think so. You know, yd if it is stay in the same kind of vertical plane, it
Yeah.
will be there. So this one should be still be the same. Iy plus e, right? 1 iq, right? Something like that.
Yeah.
Plus ny modular ny.
Yeah, and
so
y.
we can still take this one, right?
Yeah.
And
then-
the xd will be the ix. I'm not sure it is plus or minus e, the d ule, something like that, right? You
Is
know,
it the DLE or ULE?
U or D? D it should be the
Displacement? And
yeah,
then
the
U is
displacement.
yes.
The displacement.
yes.
I'm not sure it is 1 or 2 or plus or minus. I'm not sure. But this is something we talked before, right?
Yeah.
So it is, you know, if we have this box over here and this box over here, something like that, right? If we have something over here, and because this box, so this box is the one that we are considering in our program. So if we have something leaving from here to here, but we are talking about this one and this one are almost identical.
Yeah.
So it lives over here, very close to the, a little bit close, like 40% to the right, but it comes into this one
Yeah.
over here, right?
Yeah.
So that is but look
Yeah.
at I'm a little bit not exactly sure.
Okay.
Either it is plus, either minus,
Or minus, yeah.
right?
I will check.
Either it is 1 or 2. I'm not sure. 1 or 2 depends how you define,
Yeah.
right?
Yeah.
And we use what? It is L or
For which one?
for the distance here. There is a distance
Yes.
here.
L.
L.
Yes.
Right?
We use L.
Yeah.
Yeah.
L and this one it should be something like the U, right? And
L,
the T, right?
Yes.
And U it would be twice of gamma and Z something, or sometimes they use NY,
L
right?
Y. Yes.
Something like that.
Yeah.
Those things are existing
Yes.
in the paper, right?
Yes. Yes.
So so it is plus or minus or something L. But this equation should be somewhere in the paper, right?
Okay. Yeah.
So going up, I'm not sure it is plus, another one should be minus.
Okay.
You get them fixed.
Yeah.
Okay. So that is the new this is the new position, right? This basically it is the shifted x what you are
Okay.
talking,
Oh.
right?
Yes.
So this is supposed to coming back, and if we look at here, so basically this one should be a lattice node, right? And this is the ix, and now here, so this is the ix, it is the integer,
Yeah.
and here it is the xd, and this could be very
Real.
likely a real number,
Yeah.
right? And once over here, with that, the xd calculated, and then now you can have, and now you have the, you can find, the left node of xd, right?
Yeah.
And the right next node of xd, right?
Yeah.
And then you have the a you have the B,
B,
right?
yeah.
And then you will see, I'm not sure you use this one, take NL, N left, right?
Mm-hmm.
And this one, let me say N right.
Mm-hmm.
And then we get A and B, and
Yeah.
then we will have the function value, right?
Mm-hmm.
And it should be in the same direction because it doesn't change, right? And new position, it will be NL
Yeah.
and YD,
Uh-huh.
ZD, right?
Yeah.
And this one, it is a plus equal to, remember we play this
Yeah,
trick,
yeah.
put those things as zeros,
Yeah.
right?
Mm-hmm.
And you must put them zeros before, otherwise, because from the propagation, this one already have some values. This one already have some values. So you may want to do, let me show you. You know, let's finish this one. We will come back to clean those guys first. And so this one will be, I'm not exactly sure. Again, A is for which one, B is for H1, right? And it could be A, and then it is F temp, right?
Yeah.
And this one will be IQ, and IX, IY, IZ, right?
Yeah.
So that is, you know, and then we have the F, same thing, IQ, and right?
Yeah.
And YD, ZD, it should be because it must be along the same line, right? And this one should be B times of the F temp, right? And from the top, right?
Yeah.
Right? So doing this one, basically we finish from the top to the bottom, right?
Yeah.
Do the similar thing to the bottom. And those things should be set as zero.
Okay.
Because after the regular propagation, this guy already have some values,
Yeah.
right? To the regular periodic boundary from top to the bottom. So they already have a 0.12, and if you add something on top, it is not correct, right?
Yeah.
So you need to clean it up. So that means, you know, either we say we have one function to the, you know, up crossing, one to the bottom crossing. Can I erase this one? Yeah. And you may want to add one. So after the propagation, and just do the kind of set zeros to those, you know, regular z direction things. Okay, you may say it is a void set f I'm not sure. You just you know, put some you know, right? So just set zero. So before that, and so this one it should be what we do. You know, let's say for the top one. For the top one, so z will be nz minus 1, right? And so when we are talking, this is the top boundary and this is the top nodes. And for those things, after the regular propagation, we have those things. So we already have some values for this direction. And we know those are not correct because they come back from here. The regular propagation goes this way. So they have the values, and later on we are going to do the interpolation and shifted interpolation. So we need to put them to be zeros. So what we can do, and then for sure, Ix will be from 0 up to Nx, and Iy will be 0 up to Ny, right? And but Iz will be fixed on the top row. So we do the, again, IQ, and we exclude 1, 0, right? And what kind of features in common of those things for those three. Why this three? This guy need to be fixed. But not this one, but not this one.
Yeah.
What kind of difference? Why you pick this three? Because
it's in the top layer, right?
this is the top layer. This guy is also on the top layer. Do we need to put this one to be 0?
No.
So how can we separate or distinguish from this one, this one, this one, and this one?
I see.